Okay, so let's say I want to find a straight line, but I want this straight line to have a specific property. And this property is that this straight line must contain a given point. Say, call this point x0. But I also want this straight line to be parallel to a fixed vector v. Now, to get the equation of this line, that's what Theorem 1 is all about. So Theorem 1 tells me a way of doing this. So if L is a line in R2 and R3 that contains the point P0, now in the textbook they call this point x0, all right? And this line is parallel to the given vector v. Then the equation of the line through this point x0, all right, x0, okay, and the line that is also parallel to v through the point x0 is given by that equation there, where t is a real number. Now this equation is called the vector form of the straight line. Okay, now how do they get this? Let's look at R2 as an example. So here you're given your vector v. You're given your vector v. All right, and here you're given a point. Call that point, like I said, call that x0. So it's the point x0, y0. And here, let's take another point, arbitrary point, call it point P. Okay. Now, what I want is, I want to find all points x, y that have the following property. Right, so if you look at, let's call that point Q. All right. So what you want is, remember that the vector, if you look at this vector here, that vector, remember we said, is the vector x minus x0, y minus y0. Now, I want all x's and y's such that will cause this vector QP to be parallel to the vector V. So for QP to be parallel, for it to be parallel to V, we need, what do we need? We need a real number, t, such that QP is this real number times this vector v. Okay. For some t. A real number t. All right, so that translates into the following. It's all points x, y, such that x comma y minus x0 comma y0 is a multiple of that vector, and so that implies that you get that that implies that we get this right vector equation. Okay, so that is the vector form of the straight line that contains the point x0 and is parallel to the given vector v. Okay, now the equations we generate by writing each component in terms of the parameter. They are called the parametric equations of that particular line. Okay, so these are the parametric equations of that particular line. The parametric equations. Okay, so those are called the parametric equations. Now, Theorem 3.4.1 has an analogous definition in Rn. Okay, so you can basically use the same argument to include 3 or more dimensions. And like I said here, the geometric interpretation is lost for the dimensions higher than 3. All right, so here they ask us determine the vector and parametric equations of the line in R3 that goes through the point 103 is parallel to this vector, and also identify 2 different points on this line. So now it's just an application of what I've done up until now. So there they give me the vector v, and it's the vector 2, 5, minus 1, okay, and they give me the point x0. It's the point 1, 0, 3. So I want the straight line through that point, but I want it to be parallel to that vector. So what do we need? Okay, so we need to find all points such that we need these points to satisfy the following. That vector form needs to be equal to this vector form plus a scalar multiple of the vector v, which is basically the same as saying you want all points to be the same as this point vector, right, plus the vector t 2, 5, minus 1, and basically alright, so that is my vector form of my equation. So my parametric equations, are for the x component, we've got this equation. For the y component, we've got that equation, and for the z component we've got that equation. So those are the parametric equations. So now they ask us just to identify 2 different points on this line. Okay, and we already have our parametric equation, so it's easy to identify 2 points. Alright, so 2 points. So 2 points on the line on this line, right, will be, so let's take one of the easiest, is make t0, so that's going to be a point 0, 3, and that, when does that occurs? When t is equal to 0. And another point is, let's choose another one, let's make t 1, so that's going to be 3, 5, and 2. Okay, so that occurs when t is equal to 1. Okay, so it's not difficult to do. Okay, that brings us to the next theorem. Again, let's say now we looked at straight lines and we want to move on to planes. So suppose I want to find the equation of a plane, and this plane has the particular property. Firstly, it must contain a given point. Call this point x0, right? And on top of that, it must be parallel to two given vectors. Call them v1 and v2. Now that is the whole aim of Theorem 2. So now we're not dealing with a straight line, we're dealing with a plane. So let W be a plane in R3 that contains the point P0. Now in the textbook again, let me just fix that. In the textbook again, this point is called the point x0. Okay, and we want this plane to be parallel to the non-collinear vectors v1 and v2. Now, for two vectors to be non-collinear, it means they're not parallel, or the one is not a scalar multiple of the other. Then the equation of the plane through this point x0 that is parallel to both v1 and v2 is given by this equation here, where t1 and t2 are real numbers. And again, this is called the vector form of the particular plane, of the equation of the plane, the vector form. Okay, now how do they get this? So now you've got two vectors. You've got the vector v1 and you've got the vector v2. Okay. Now I want the following. What I want is firstly, I want my plane to contain this point x0. Okay, call that the point x0, y0, z0. Okay, and that's the point I wanted to contain. So basically, again, so you're given the point Q there, and you take a point P, any arbitrary point. Not that it's completely arbitrary. It's arbitrary, but it has to have the following property. Now you want this. You take again this vector, and now what I want is I want to take this vector, which is this vector here. So it's x minus x0, y minus y0, z minus z0. Okay, and I want, what do we want? We want the vector QP to be parallel to V1 and V2. Okay, so what do we want? Again, we want that vector to be parallel to both. All right, so again, we want QP, so we want the point x, y, z to satisfy the following. It will make this vector QP parallel to vector V1. Okay, so there's a scalar alpha 1 that will make this vector parallel to that, and we also want alpha 2 to be. We also want V2 to be parallel to QP. All right, so for where both alpha 1 and alpha 2 are real numbers. Okay, so now what do we have from there? From there, if you take that vector equation, if you add the two vectors on the left-hand side, okay, you get twice the vector QP, and that is going to be alpha 1 V1 plus alpha 2 V2. Sorry about that. All right, so that then is going to give you the vector QP is going to be a half alpha 1 V1 plus a half alpha 2 V2. All right, so that is then just going to be, what's that vector? It's going to be the vector XYZ minus X0, Y0, Z0. And that is going to be T1 V1 plus T2 V2. Again, you can call that half alpha 1 and half alpha 2. You can just call it T1 and T2. T1 and T2, these are both real numbers. Okay, and that's then going to imply that that X is going to be X0 plus T1 V1 plus T2 V2. All right, so that is that is, like I said previously, if you go back here, the equations that we generate by writing each component in terms of the parameters are called parametric equations of the plane. And again, Theorem 3.4.2 has an analogous definition in Rn, although the geometric interpretation is lost in dimensions higher than 3. All right, so those are the parametric equations of a plane that contains a given point P, and it is parallel to two given vectors V1 and V2. Okay, so let's look at that example. Determine the vector and parametric equations of the plane in R3 through the point 1, minus 1, 0, that is parallel to those two given vectors. So now if we look now at our parametric equations, so let's take the vector x, and we know the vector x is the vector x0 plus t1 v1 plus T2 V2, and so therefore remember we said X is this point, or this vector, see it as vector, and that is going to be equal to the initial starting point that you want that vector to plane to contain. You want this point to be contained, and you want it be the sum of the scalar multiples of two vectors v1 and v2, where v1 is 2, 0, minus 1, and the other vector is that one there, which is 1, 1, 1. Okay, so the parametric equations are, the parametric equations are the parametric equations are so x is this equation here, it's 1 plus 2t1 plus t2. Y is minus 1 plus 0t1 plus t2. Okay, and z is going to be 0 plus minus t1 plus t2. Okay, now they just ask us identify two different points on this plane, and that's not difficult to do. All right, so we can these are, we have now the parametric equations, so we can just choose 2 points on the plane. So I'm just going to choose 2 points. So let's look at the point, basically the point 1, -1, and 0. And that occurs when T1 is equal to T2 is equal to 0. So that's one point on the plane. And another point on the plane, let's choose this one. We choose T1 to be 0 and T2 to be 1. So that is going to be 2. That's going to be 0. And we chose T1 to be 0 and T2 to be 1. So Z is going to be 1. Okay, and that occurs when T1 is 0 and T2 is equal to 1. So these are two points on the plane. Okay, arbitrary points on the plane. All right, so there in the first example, we are basically asked to determine the vector and parametric equations of the straight line through those 2 points. Okay, how are we going to go about in doing this? Okay, so we've got the point, the one point is the point 1, 2, and the other point is the point -1, 1. Okay, so we're going to call this, so let's call that P, and let's call that Q. Okay, so we're going to call the vector V as the vector PQ. Okay, and that is the vector -2 and -1. Okay, so that is that vector V. That's the vector V. Now we want the straight line to contain both the points P and Q. So we want the straight line, well, we want it to contain this point here. And we want to find, so what we're going to do is we're going to let x0 be my starting point, the point that my straight line must contain. And we want to find all points x, y. So we want to find all points. We want to find all points x, y such that right. So we want to find all points x, y such that x, which is this point that, well, you can see it as, because we're looking for the vector equation, we want it to be equal to x0, okay, plus a scalar multiple of the vector v. So we want to find all x's such that that's the initial point, plus scalar multiple of this vector -2, -1. Okay, so that is the vector equation of a straight line through those 2 points. Now the parametric equations are, so the parametric equations are, so the parametric equations are basically x is going to be 1 minus 2t, and y is going to be 2 minus t. So those are the parametric equations of the straight line that goes through both the points 1, 2, and minus 1, 1. All right, next we are asked to determine the vector and parametric equations of the plane through those 3 points. Okay, so we asked that. So we need to do something now. So we're given 3 points. We're given the point 1, 2, 0. And there we're given, so call that point P. We're given the point minus 1, 1, 0. And we're given the point, okay, so let's call that point Q. And let's call this point R, which is the point minus 2, 0, 1. So we want the equation of the plane that goes through those 3 points. Okay. So what I'm going to do is I'm going to call this vector, I'm going to call that vector V1. And I'm going to call this vector V2. Alright, so again what we're going to say is let V1 be the vector PQ. Right, let V2 be the vector PR. Okay, and let your initial point that you're going to start off with is the point 1, 2, 0. Okay, so to find the equation of the plane, we need to find all points x, y, z, such that remember we said that we want x, this vector, to be the same as that vector, plus t1 v1 plus t2 v2. Okay. For t1 real number and t2 a real number. So, I mean, we want to find all x, y, z's such that you can express x, y, z as the sum between the vector x, x0, okay, plus that vector there. Okay, that is what we want. That is what we want. All right, so it's basically so it's all vectors x such that x is expressible as your initial point, which is the point 1, 2, 0. Okay, and it is plus t1, which is the vector v1. And what is the vector v1? It's the vector pq. So that's minus 1, which is minus 2. It's 1 minus 2, which is minus 1. And it's 0 minus 0, which is 0. Plus t2, what's the vector v2? It's minus 2 minus 1, which is minus 3. It is 0 minus 2, which is minus 2. And it's 1 minus 0, which is 1. Okay, I just want to make that more clearer. Right. Okay. So what are the parametric equations? Okay. So what are the parametric equations? So the parametric equations. So the parametric equations are what? Parametric equations are for x. We've got it's 1 minus 2t1 minus 3t2. Okay, your y of your plane component is going to be 2 minus t1 minus 2t2. and your z component is going to be basically T2. So those are your parametric equations of your plane that contains the three mentioned points. All right, next we have linear systems. Okay, so this theorem is just a quick connection to what we've already done with the dot product. So all this says is that if A is an n by n matrix, then the solution set of the homogeneous linear system, Ax equals 0, consists of all vectors in Rn that are orthogonal to every row vector of A. Now, to see this, right, if you look at this matrix A, right, now the matrix A we said is it's an m by n matrix. So it's an m by n matrix. It's got m rows and n columns. Okay, so it's got n columns, right? Okay. Okay, so it's got n columns. So it's got n columns. Now, if you look at the vector x, right? So an m by n matrix multiplied by a column vector x, how many rows must x have? X must have n rows, okay, because it's m by n times an n by 1. Okay, so you're multiplying m by n with an n by 1 matrix. Okay, so for that to work, you need these two to be the same. Okay, now what happens if you multiply? What happens if you multiply, as an example, what happens if you multiply that row, okay, with this column here? Okay, now if you multiply that row with a column, so let's just make that, right, make those blocks red so you can see, okay, and just for argument's sake to see it clearly, let's make those blocks yellow. Then if you multiply that a row with that column, then you're going to get these blocks. Okay, this is just an illustration so that I don't have to write everything out. Okay, and you're going to have these are going to be from your column vector, and you're going to have the others from your matrix A. Okay. So what does this remind you of? What is this? This is basically the dot product. Okay. It's the this here is basically the dot product between which vectors. It's the dot product between the vector that I'm just going to again do the same so you guys can see. Again, that's going to be the dot product between those two vectors. It's easy to see that. Right, it's going to be the dot product between those vectors. Now, because we're working with that system there, so you want that to be the 0 vector, okay? So you want that to be the 0 vector. So basically, this particular dot product here needs to be 0. So what a solution to this homogeneous linear system is, it's just it's all vectors in Rn. So we're talking it's all vectors in Rn that are orthogonal to every row vector of A. And because essentially the product that you work out, which is this product here, you can see that as a dot product between a row vector and a column vector. All right, and that has to be 0 for each row that you multiply. For each row that you multiply with this vector here, you're gonna get a 0 quantity, and we know that two vectors are orthogonal when their dot product is equal to 0. Okay, so it's easy to see why this theorem 3 holds. Right, so this theorem gives us a way of finding the equation of a straight line going through 2 points. Now, we already sort of touched on this in a previous example. So if you're given 2 points, then I want to find the vector form of the line containing x0 and x1, and it's basically that form there. Now, how would you see that? Well, it's an application of the first theorem we did in this section. So you're given 2 points. You're given the point x0 and you're given the point x1, and you want to basically form the vector v, okay, which is that vector v. It's the vector v, and the vector v is is x1 minus x0. Now, right. So for a point x to basically to lie. Now, this point x is a point in Rn. Now, for this point x to lie on a straight line, the straight line. And this straight line containing both x0 and y0, or x0 and x1, what do we need? Okay, we need this point to satisfy this vector equation. So it's basically going to be x0 plus it needs to be a scalar multiple of the vector v. Okay, and that is going to be x0 plus t minus times x1 minus x0. Okay, so that is that's a vector form of the equation of the line containing those 2 points. Okay, so Theorem 3.4.4 just says the following, is if you have this linear system and we want to find the general solution to that linear system, then we can do that by just taking a specific solution. You can choose a specific solution of Ax equals b, and all you do is you just add that specific solution to the general solution of this homogeneous linear system. Okay, so you can find the general solution of Ax equals b by taking a specific solution and adding that to the general solution of Ax equals b. Now, you can easily quickly see that. We're going to run through why this is the case. So what you're going to do is you're going to let x0 be a specific solution. A specific solution to Ax equals b. Okay, now first of all, we want to see what a solution to Ax equals b looks like. So what we claim is that we claim that the general solution, the the general solution set of AX equals B is given by this set, okay, where W is the general solution set of the system AX equals 0. Now to prove that the general solution to prove that this is the if we go back to that, to prove that this is the general solution set is the general solution set of AX equals B, you need to simply just prove that that every point within that set is a solution to AX equals B. Right, so we can easily do that. So what you can start off with is you can take a point and you can take it within that set, and let's just check that it's a solution. Now it's easy to do that. All you do is you take that point, you plug it into your system, and that is then going to take its course, AX0 plus AW. And what is this? X0 is a solution to the system AX equals B, so that's going to become B. And what is W? W is in there. And what is that? Remember, we said that W is the general solution set of this system here. Okay, so it means that this W is within capital W, so it is going to be a solution. So that's going to be to this system here, to that system there. So it's going to be 0. It's going to be 0. Okay, so hence X0 plus W is a solution. It's a solution to AX equals B. Now, to complete the proof, all we need to show that every solution, to this system can be written as a point within this set. Okay, so it's expressible as a point within that set. So okay, so to do that, all we do is okay, so now let X be any solution to AX equals B. Then you can write X as basically, you can write X as X0 plus X minus X0. Okay, we haven't done anything there. Now what I'm interested in is that. So what I'm going to say is note that what happens if you plug X minus X0 into that linear system there. Okay, right, so first of all you get AX minus AX0, and what is AX? We said X is a solution to AX equals B. We said X0 is a solution to AX equals B, so therefore we have that. Continuing on, hence X minus X0 is in W. Alright, because x minus x0 is a solution to which system again? It's a solution to that system. Remember what we said. It's a solution to that system. So thus you can write x as x0 plus w, where this w we said is x minus x0, which is in w. Okay, so that means that you can express every solution of ax equals b. You can express it as x0, which is the specific solution of ax equals b, plus another vector w, where this vector w is a solution to the system ax equals 0. So basically the general solution set of ax equals b is just a specific solution. Choose it, any one x0, and you just add that solution to every solution in the general solution set of ax equals b.